Yes, good morning and a warm welcome. Everything that has been said already is true, specifically the part with the timing. So I will try to convince you to give me more time than that was planned. Today I want to talk about two things, namely have a look back of what we did, and that might relate to the issue that we have here of interactive music. And second, what we are aiming for and what we are planning to do. So first, I start with the retrospective. It was in 1976 when Steve Jobs started to create a technological system called a computer and attempting to sell it to a broad audience. And that was somehow delayed due to the malfunctioning, so that in January 77, a competitor, Commodore computer, came out with the first personal computer in the market ever. Am I doing this or is this someone else? So can I ignore this? Yeah. And later on, the summer in 1977, also Steve Jobs came out with his system, and then IBM came out with what is known as the personal computer, a multi-purpose computer whose size and capabilities and price make it feasible for the individual to be used. And it is intended to be operated directly by a user. Up until then, computers were operated by technical experts. And this computer made it to the face of the Time magazine in 1983 as the computer being the machine of the year. Since then, selling rates were growing. Here you see the evolution of sold items on a planetary scale. And we see that this tendency of ever increasing sales had a turn in 2011. And the reason being that more mobile devices came into market, and in 2015 more tablet computers have been sold as compared to personal computers. If you look at personal computers in more details, 3.2 billion on planet, 1.3 billion tablet computers, 600 million smartphones, smartwatches, 1.3 billion cars on planet, everyone driving with a navigation system, and 6.3 billion phones, mobile phones, most of them being smartphones already, are in use on planet today, with a population of 7.3 billion humans. So almost everyone is equipped with that technology. If you look into the interaction of this personal computing paradigm in more detail, we see that there are keyboards, and there are trackballs, and there are mouse devices, and there are pens and styluses and microphones. And this defines the interaction principle with those computers, namely that they are in the passive role while you as the user are in the active role. And in the active role, meaning that you provide input and then the system reacts with some output that has been computed. But you are the trigger, you are the active part of the interaction. And this has not changed. This is true for all the personal computing technologies that we see today. It is called the explicit interaction. And explicit interaction also happens in the musical domain with all the instruments. Those instruments, they are interacted with by using fingers and hands, or lips and the mouth. And it is explicitly and intensively that you play that instrument, and this is what the instrument gives you as the output, namely the music that you perform. Okay, so this is this generation of explicit interaction. It has been by Leon Theremin in the 1990s, who invented a machine which used the body mass of a human being as the ground mass for a technical system, and two electrodes, basically two antennas, to control the frequency of an oscillator as well as the altitude of that signal, and the signal being propagated to a loudspeaker, and here is the result. And the result is that interaction with that musical device is being done touch-free. So here is...
Электромузыкальный инструмент термин-вод — это первый инструмент такого типа. Это песенно-голосовой инструмент. В нем управление мелодией достигается посредством влияния на электромагнитное поле около инструмента.
So this is well known. It is completely touch-free. It is without touching the instrument that music is generated. Here we see Alexandra Stefanova. She was performing for the NBC in 1931, and then there came a tour through all these US-American places to present the new instrument, and it generated much attention at Carnegie Hall, as for example, or the Metropolitan Opera House. So that was somehow the start of something that even finds its continuation today. So here we see Katica Iliemino. She is performing the and you know how it goes. So this is somehow also related to computing, namely to this big issue of pervasive computing. Pervasive computing means that it is not that computers would be everywhere on planet. It is that everything is a computer. So all these these appliances of everyday use, like sunglasses and shoes and belts and bracelets and cars and seats and cities and even the whole planet appears to be a computer. And we have built all these computer systems embedded into those everyday appearances with a variety of projects. So this is the history of projects that range from the nationally funded FFG up until the Frame Program 7, up until Horizon, etc., international research projects. And we have created all these systems that you see here in a symbolic representation, more or less in their function. Why and how could we do this? Well, one of these issues is the miniaturization of microelectronics. What can you build on 1 square inch of silicon? Here is IBM's world's smallest computer. It has 8 times 8 tiny computers in a row, and all of them are in the range of a 386 performance computer. Operated with SRAM memory and with photovoltaic power cells. There is a very topical and recent core, the Intel Core 9, ninth generation, Extreme Edition, 18 coprocessors here, with 1.3 teraflops of performance. That is about 300 times the performance that was used to land Apollo 11 on the moon. In one single dice. And there is specific or special purpose processing units out there, like the Broadcom dual frequency global positioning sensor, which is GPS, GLONASS, Galileo enabled, which uses accelerometer, gyroscopes, compasses, the barometer, etc., Wi-Fi cellular positioning to support self-learning and dead reckoning. So wherever you integrate this, you have about 5 meters precision with support of mathematical improvement, a 2 meter or a 10 centimeter precision of locating the object that is carrying this element here. There are sensors for temperature, humidity, airflow, shear, force, pressure, acceleration, light, sound, smell, etc. That all can be embedded into such a compute platform, and the NVIDIA Xavier platform is a supercomputer in itself, in one single chip that has 8 cores and that has 256 CUDA cores aligned with it. It is able to do the parallel encoding of 32 high-resolution full HD camera streams simultaneously through that chip. Okay, and this is a friend of ours. We will be referring back later on during this talk. So here is the second trend. This is the growth of global networks. We do see here the planet in 2000 and the growth of the internet on this spherical presentation. Take a cut through the equator, like you see it here. And then you have here the planet with the position of internet routers as they are located in geography, from Boston to San Jose to Honolulu to Sydney to Bangkok to Moscow, St. Gilgen, and Dublin. Yeah? And on a logarithmic scale towards the center of this drawing here, you have the emitting power of the internet routers. So the closer they are to the center, the more internet traffic they are emitting. Interesting at this time to see that the most powerful internet routers are located at US territory. And if Europe wants to communicate with the Far East, we always do this through these US routers. Okay, I leave it to your personal assessment what this could mean politically. And how this evolved in 10 years and in 20 years. So we see that the planet is almost full with access technologies to this internet. And this is the second part, this exponential growth of global networks to support what we call pervasive computing. So as for pervasive computing, there is no way of a old-fashioned and say explicit interaction. Sunglasses do not have keyboards, they do not have screens. You cannot interact them with the mouse interaction. This is impossible. Yeah? And considering that you have tens or 100 of these devices, you cannot handle 100 computers with 100 different keyboards and update the information there. This is impossible. So the interaction modality has to change. And the change here is that these objects with embedded computing technology are taking part to be the active part in the interaction, namely to use sensors that collect data, and the understanding of that data and the reasoning of that data would lead to plans, and the plans would largely yield to actions on how these things should act. And this is doing in the background without human attention. It is taking all the data, it's trying to interpret it, it's trying to best out of the data in terms of action for the human being. Okay? So they collect context, each and every piece of information that is describing the situation of an entity, like the time of the day and the geoposition and the temperature and the humidity, and everything that describes our situation here is considered context. And we have machines that can capture and understand context. So it is easy for a machine to understand that this here is a presentation setting and identify this based on the presence of people and the articulation and the voice tones, etc. So a machine can detect that this is now a meeting situation. And we can now equip all these devices and say things with that technology to do this loop of perceiving and acting autonomously. And they are all networked, so they can even be exchanging data and exchanging information in order to adopt the appropriate behavior here. Yeah? So One example that we did already in 2003 was one of these sunglasses projects with sensor units, with a voice unit, with a text-to-speech unit, with a motion unit, with a image capturing unit, with a camera, with wireless communication technologies, with even a sensor for the galvanic skin response that allowed to conclude about the stress level of the person. And we have built it with, in cooperation with the University of Southern California, and we have tested it in the sports domain, in the tourism domain, in the healthcare domain, in the fire brigade domain. And surprisingly enough, 2007 we have finished this project here. And 2011 there came a product into the market, which was referred to as GLASS, which surprisingly had many technical components in common with the spectacles platform as you see it here. And Tad Starner, the CEO of Google at this time, is a very good friend of mine. So, context-aware IT. As a second step, we can also now look at not just what describes the situation of an entity, information-wise, but also what is the activity of that entity. And if you think about you as a human being exposing certain locomotion activities like walking or sitting or standing, etc., we can think of having sensors in our shoes. And these sensors would capture the inertial parameters, the acceleration, the gyroscope, the magnetometer data, and analyze it in real time in a very tiny compute platform. You see the compute platforms are of this size here. Yeah? And then if we look at the data that these IMU sensors are generating, then we see for a straight walk, this is a person going straight along the alley, we see these patterns of acceleration. So the blue is the right foot, the red is the left foot, and we see this kind of pattern here, which is a straightforward walk. If the person is climbing the staircase, then we see that the pattern here changes a bit. Okay, so what you see with your eyes can be analyzed by algorithms, and the algorithms can immediately detect what the person is doing just from the two sensors that are embedded into the shoes. And we have built them, and we have done experiments with that. We have then moved the sensors also into watches, into smartwatches, to have the wrist-worn activity recognition, and it was presented here together with an energy provider, and we have developed also a counterpart, namely a power plug system that goes into the wall, and the shoes, they would in a wireless way transfer the activity to the power plug, and the power plug would transfer this to the counter, and that server system would respond back with switching actions to switch on and off electrical devices in the home. We were able to demonstrate that for Upper Austria, in a test case with 28 homes, real homes, we were able to identify a potential for energy saving of about 18%, empirical evidence for that. So here is just a reminder or a first or a look back into that system and how it works. I hope if the video starts, does not at the moment. Okay, we can also extend these sensors into the clothing. Here are experiments where we have knees and shoes and right upper arm, lower upper arm, the back, etc., equipped with sensors, and then we can track almost all the activities that the individual is doing at a level of some 93% of recognition rate. Interacting as an activity. This is a true picture from my home. It is showing all these remote controls that there are there on my living room desk. And I'm, not such a nerd with all the most recent technological electronic equipment in my home. It is just, it happens when you operate a standard home. And then we had this challenge in the research studios to find out about what is the remote control of the future. So what would people expect and accept as a remote control? And then we have started to look back in history, and that the publications of Napier about the movements of the human hand in the 50s already, we found out that the human hand by evolutionary steps is able to do things, namely to have a grip to hold things, which is called the power grip. Depending on the size and the shape of this object, the power grip varies a bit. And there is the precision grip, which also involves the finger cups, and depending on the object, you are able to more or less precisely tune or set a certain setting. Okay, and these are the only things that the human hand can do. So the human hand and the fingers have not been made to press buttons here. Okay, they are just here to grab things and to precision access those. So then we have started to find evidence for this. So what is the human hand doing with the cylinder? What is the human hand doing with a cubic object? It is flipping and tossing it. This gives a hint or a raise for the assumption that these could be the objects of interaction for a remote device. And we did the concept studies. So the cylinder is more continuous and the cube is more a discrete thing. So we built prototypes and we let people play with those prototypes without knowing what they are doing. So we put them on the table and we asked, use these devices without knowing what they are used for. So we experimented on this Donald Norman notion of the ability of a thing to express itself how it wants to be used, the affordance. Yeah? So, and if you take this one here, everyone started to grab it, to flip it, to toss it, etc. For this one, everyone grabbed it from top and tried to turn it and rotate it. Here, the finger of all the test persons, they came exactly into this place here. That could be the launching of an atomic bomb. They did not know, but the finger, like a magnet, went into this place here. So there is a way of inducing the activity by the pure shape of the remote control. Then we built all this. We have decided for the cube. Then we built all this electronics. We built the software for it. Here is the electronics print, at the Mega platform, a gyro, an accelerometer, etc., and the power supply. We developed a interaction design for tossing and flipping. We even built the system to operate it with a standard off-the-shelf, off-the-market TV platform. And we had this alphabet of interacting with that remote device. And it turns out that 97.3% of the activities that you are doing with your TV set at home has to do with 3 operations. One is on-off, the second is volume control, and the third is hopping the channels. The rest are not used. They are not used at all, or very, very rarely. And we also tried then to embed this into more aesthetic shapes. And in the end, we were able to remove this 6 times 92 button systems into a fruit bowl, where all these fruits had somehow the responsiveness for the video and for the TV set, etc., and the manipulations and rotations were the interaction principle for it. This has also been taken by a friend of ours, Hiroshi Ishii at MIT Media Lab, to also work on this tangible user interface. So the interface to things that you are grabbing, that you are grasping, that you are touching with your hands. And here is a brief intro to that explains how to do music by manipulating things like cubes, in this case, and rotation of cubes and the spatial movement of cubes, the placement. So all of this has kind of a background activity for controls of synthesizers and generators and modulators and so on, which allows the whole system to be used as an instrument. Yeah? So that is somehow the intensive interaction in order to generate music. There is also kind of a an implicit interaction for making music, which is demonstrated in this example here, where the same kind of sensors that we have in our shoes for activity recognition are here placed on the body of a dancer. And these are collecting the motion changes of that body. And these are transferred wirelessly to a piano, and the piano is generating the tones according to the movement of the person. Yeah. So this is also a way of recreating the way how we interact with musical instruments. Okay, yet another idea what came up then was human attention. So we know attention is defined to be the taking possession of the human mind in a clear and vivid form of something that is in the focused interest by keeping aside all the other things that are not in front of this focal interest, withdrawing from things that are not of interest. This idea by William James has been continued some 70 years later by Herbert Simon. He was a Turing Award winner in 75 and a Nobel Prize winner in 1978. And he was an economist. He was defining and inventing new theories on how people make decisions when they do not have complete information. Yeah? So if there is just the boundaries of rationality available on the data, how would people then decide? As there is no way to get full information to have the full base for this decision. So he invented this boundary rationality theory, and he once formulated that we are, with the growth of information, with this growth of media, with the internet was not available there, but with the printed information, with the TV information, etc., we are exposed to a wealth of information which creates on the other side the poverty of something that is needed to work on this information, which is the poverty of attention. So you see the economists behind it here. So there is the wealth on the one side and there is the dearth on the other side, and the relation in between here somehow is a discrepancy. So he defined then what is called attention economics. So considering human attention as a scarce resource, and that is also part of our work. We then had implemented systems that attempted to analyze how much attention is a spontaneous bypass on a train station, on an airport, to a public display. How attentive is that person to what is being displayed here? And we have looked at the body pose with sensors. We have looked at the motion. We have looked at the orientation. We have looked what the shoulders and what the head are doing, what the eyes are doing. And from this we can read off the amount of effort the person is allocating towards this piece of information. And we have conducted experiments that explain how this attention is allocated. Together with this attention, we have also then looked into cognitive load. Cognitive load is somehow expressing how concerned the human individual is with respect to the perception through all the senses. If we take just the eye, we do know that there is an indicator for this perceptive amount and the cognitive load, which relates to the pupil diameter. And the pupil diameter is in change. It is controlled by a specific part of the human brain, the locus coeruleus, which is responsible for controlling the contraction, but also the dilation of the pupil. Yeah? So there we found out that very much information about the expertise a person has in a certain domain is expressed with the eye. And the eye has dynamics that are defined based on fixations. This is when the eye is fixing a certain point, and then it jumps to a second point, and the third and the fourth point, which is a scan path, which is then a trajectory of saccades that the eye is following. And there we found that this pupillary activity and the cognitive load analysis related to it comes from these physical properties that the pupil dilates in between 4 and 8 millimeters, depending on effects and stimuli coming from the outside. And there is one effect, which is, of course, light. The more light, the more bright the scenery is, the more the pupil will contract. The darker it is, the more it will dilate. So there is a pupillary light reflex, if you want, and some 80% of the contraction is responsible and due to this pupillary light reflex. On the other hand, but there is also an overlay with a second effect, and that second effect is coming from cognitive load. So this is superimposing the pupillary light reflex, and this is called the cognitive load response. And it is minor with respect to the effort, is some 20% that is responsible in the absolute change of the pupil diameter that goes back to this second effect. And it was Benedict Golan who in his PhD analyzed this separation of these two effects, namely the pupillary light reflex from the cognitive load response. And this was conducted with an experiment of an industrial worker doing some 50 workpieces in a certain order. And here we see the average pupil dilation over this averaged over these 50 experiments. And we do find that when that person is grabbing an element, grabbing a tool, grabbing a workpiece, the pupil tends to contract because it is relieving cognitive load. And there are work steps where this part that is taken has to be placed precisely somewhere else. The opposite happens, namely for the placement task, all these effects coming from cognitive load are expressed by an observed pupil dilation. So the pupil is dilating the more cognitive load that person is experiencing, which is a very nice result, I think. And then we have used this to design systems that would automatically, while in operation, track this pupil dilation. And we have built systems, physically built them, and exposed it to experiments. Here is one of the more recent designs that we have. The leap sensor integrated, the depth cameras embedded, a high-performance compute platform, belt worn in this case, vibromotors for feedback, and an eye tracker, as you see it here, that would always look into the eye and from that deduce the cognitive load or the activity of that person. Here is an application case that demonstrates by using this platform how the 3D scenery of a certain, in this case, manufacturing hall is captured. The point cloud that is generated based on these depth images as they are coming in real time. And by just looking at things, we can build up a whole 3D world model of that scenery. So this is in effective operation and has served for real practical applications in industrial settings. We have also exposed this in this welding domain. Welding is a crucial thing that from time to time has to be done by hand. This is a person doing the welding, but being at the level of a beginner. Looking at the pupil dilation here, we do see that the pupil is very wide during these welding experiments in these different welding steps. Welding steps are very irregular, which is indicative for a beginner in this case. And the more advanced the individual gets in handling these welding tools from the intermediate to the expert, we see that the pupil is getting more and more contracted or released, cognitive load is disappearing, and we can read off the expertise level or the skill level of an individual just from the pupil that we have here. And then we have a lot of further experiments and systems done. One is supporting individuals to escape from critical situations, like emergency situations. The approach here was to have a belt, a life belt, as we call it, equipped with tactors, and those tactors would vibrate in order to indicate the path to the nearest exit. Okay, so intuitively, the amount of vibration, but also the directionality of the vibration would guide a person from a critical situation to the exit. As a kind of a navigation system where you cannot look at the computer screen because there is no light, because it's dark, and also the sense of hearing, the auditory perception is superimposed by the noisy environment and is not effective to deliver information to the individual. But the vibrotactile channel is still open, and this is an answer to deliver information by the vibrotactile channel to the individual. For Linz Bahnhof, in cooperation with Österreichische Bundesbahn, we were able to demonstrate that in a situation of having to evacuate some 7,000 people from that train station, we were able to reduce in a simulation the amount of evacuation time by 28%. So sociality, yet another domain. How can systems be aware of the social interconnect of an individual? Well, here we can step back to a well-established platform, which is a smartphone. The smartphone itself is a multi-sensor. It has sensors for ambient light. It has 2 cameras. It has 4 microphones. It has a GPS orientation accelerometer, etc. Sensor built in, a digital compass, a positioning unit. And taking this information, we can say much about the social interaction of individuals. So here we have analyzed individuals in mass situation, in mass entertainment events, in mass sports events. This is the Lord Mayor show in London, where we have built an app that can be downloaded by the spectators, and the spectators are open and willing to deliver and provide their GPS data while they are present in this event here. So you see River Thames here, as for example, the Court of Justice, King's College, etc. And there you see these density maps, which are indicative for the amount of people available there per unit square space, together with their movement directionality, which we refer to as speed. If we look into how much of this speed is going in different directions, the variation in the orientation, if you want, we get something that we call turbulence. And if we multiply the two things, we get an expression for pressure, which is somehow the dense, chaotic style in such a mass. That is indicative for a potential hazard where the mass event possibly turns into a mass disaster, as we had seen in several cases already. And here we have done this here in Austria with a huge sports event, 40,000 athletes, 200,000 spectators, some 25,000 apps downloaded, used during Vienna City Marathon by spectators and even athletes. Here you see how these social interaction dynamics evolve over time, and how security and safety issues can be supported using this information in real time. So here we have a situation where the sociality is used by an application, and therefore it's called a socially aware system. Yeah? At this time, when I look into the audience, I see a picture like this, usually. So everyone is asleep, more or less. Why is this? Well, here is the answer. It has to do with your attention span. It has been studied that the attention span focused in an experiment in 1998 was some 12 seconds. So how long you are looking at a picture, how long you are inspecting the title of a newspaper, how long you are focusing an image on your smartphone, etc. 12 seconds. But this has gone down in one decade to 8 seconds in 2008. Yeah? And the goldfish that you've seen here has an average focused attention span towards food for about 6 seconds. The sustained attention span is the more focused, the more oriented, the more sustained type of attention. This has dropped from 12 minutes in 1998 to 5 minutes in 2008. And we do not know where we are now. Namely, it could be that due to this tsunami of information, this information flood that is coming also from the internet, that is coming through our smartphones, through all the bells that are rings, all the pictures that are presented, all the Flickrs, all the YouTubes, all the Facebooks, etc. Yeah. Our attention span has considerably dropped. It is 4 seconds. And the sustained attention span possibly is 2 minutes. I would assume. We don't have empirical evidence for that, but I would assume. So, pardon me? Is now. Is the attention span here, sustained. Okay, yeah. So, but out of these 40 minutes, I guess after 2 minutes, I have lost you. So I've checked. After 2 minutes, the first people started to, do emailing, do Facebooking, posting something, doing smartphone interaction, writing SMS, etc. And it happens. You cannot prevent from it. So whenever you give a talk, this will happen. Yeah? You have to live with it. So what is it that you can do? Usually in a keynote presentation, as I do it here, there is a start, the introduction, everyone is somehow intrigued what will happen, attention levels are climbing, okay? So this was the truth when I started to talk about the personal computer, and this was sustained when I was talking about these interaction modalities and the theremin, etc. And then these components, and then there came this disruptive element to your attention. Yeah? Yeah. So it had nothing to do, it was just to get back your levels of attention. And indeed, this is measurable, so that from this point on, you are again more open to take information that is following. Okay, so. So far about the get you back to attention friend here. And this is somehow the summary for the evolution of aware IT, namely that we have IT that is observing, and from that actively proposing action that you are then accepting as a human being, but not inducing it. So it is protecting activity and attention, energy, as it is coming from the background, and it is calm and non-obtrusive. And we could add way more bubbles into this here. And I have, how many minutes do I have? 1 minute? Oh, then this will not work. So I would have told now a story about Alan Turing and machines. He was developing this Turing machine, which defines all the problems that we can solve with computers here. But he also raised these questions whether machines are able to think. Can machines think? So this issue of thinking machines. And even the Time magazine had this question in '96, can machines think? And we know that in '97, Garry Kasparov, the reigning chess world master, was beaten by Deep Blue, a computer program. And an even more complex game like Go was demonstrated by the company DeepMind, the London company DeepMind, with AlphaGo, a program to defeat the world reigning Go master. And even for these non-structured types of games like poker that demand intuition and they do not have structured information at all, computers have now delivered victory over human beings. These are the world's fastest computers that we see and that we have. And it is interesting, the New Scientist once wrote that these supercomputers are not thinking machines. They cannot think. But this biological tissue here, this group of cells here, is a thinking machine. And the idea behind here is that each and every computer of the world is somehow a compound of a processing unit and a control unit. And on the other hand, has a memory. This is the so-called von Neumann architecture of a computer system. And all the computers that we have on planet today are built according to this principle. So processing is separated from memory. But in the biological system, if we take this, the neuron, for example, we have the soma and the axon and the dendrites and the interconnectivity of these neurons with neighboring neurons at a massive scale. 10 to the power 14 neurons we are said to have in our brains. And these are interacting with each other on an electrochemical basis. And there the principle of storing information and processing the information is one and the same physical thing. It's not separated. And maybe this is the reason why these are the things that are able to think. And there would be some further explanation to it. Then I would have, may I make this experiment here? Here's a piece of music. Raise your hand when you recognize who is the composer and who is, and you can give the title. So Professor Gutjahr will tell us what this is. It is Dimitri Shostakovich, Waltz number 2. Yeah. And then I would have asked the question, now that you are trained to identify the composer, 3 pieces very quickly. So who is the composer here? Okay, keep it, take a note on your notes. Second, batterie fast leer. Huh? This is some Shostakovich-like, at least. And here's the number 3. Who knows about number 3? Who can name at least one composer? Yes?
I think the second example is probably an AI composer played by Mozarteum, and the third one seems to be some deep learning based on visual impression.
Yeah, so the answer is the first has been composed by AI, the second has been composed by AI, and the third one has also been composed by AI. We do see that computers and their way of thinking are already used, to create, to compose, to do the creative part, not just the compute part of a task. Yeah. So and then I would have talked about the Künstlerhaus and the Ringstraße and this monumental epochal, understanding of art in Vienna at the fin de siècle. And then I would have talked about a group of individuals not going with this well-established traditionalism and bring in some liberated modernism into it. And I would have talked about Loos and Koloman-Moser. And that would have been the last thing then, namely the the Vienna Moderne, namely that was the poster for the first exhibition of the Wiener Secession, which was a counter-argument against the establishment by young, future-oriented artists. And Gustav Klimt did the poster for it. Here you see this poster. There is this symbolic fight of the Minotaurus against Theseus. So the new and the young and the fresh fighting against the established. And you know how this fight went out, how this resolved. And here is Pallas Athene watching this, and here is the indication for the exhibition. And there is empty space, indicating simplicity, going away from complexity. And by intent, this was here left open by Klimt. That was not presented to the public, but this was delivered to the public. Did you see the difference? No. Again, that was the original, and this was the publicized after censorship still. And it was what Klimt was fighting against, and his group at the Secession. So at this time, at the fin de siècle, we had an understanding of art that has to take over all the different aspects beyond painting pictures. This is what Rector Gutjahr has started with in its speech, namely that the artist, as it was claimed here, has to also look at all the situations where we live, how we have, how our homes are furnished, how the walls are painted, etc. This is also an issue for an artist. And Wiener Moderne claimed this as the Gesamtkunstwerk, and the Wiener Werkstätte was somehow dedicated to do all this. And I would like to draw this parallel that pervasive computing in some sense is also attempting for this Gesamtcomputer, as I would call it, namely that the most profound technologies are those that disappear. They weave themselves into this fabric of everyday life until we cannot distinguish from it. So it is a design issue as well, the Gesamtcomputer, which is also a musical computer to a high extent because it also concerns very important aspects of our life. Thank you very much for accepting this long delay in my speech. Thank you.